So notice that we proved this nice system and we were able to, so there are two things to differentiate, right? We had a general multiplicative weight update methodology, right? Which basically had some probability vector at each round, defined some what you call cost vector or regret vector, whatever you want to say, and updated the weights in a certain way, right? But then we specialize this to covering and packing, solving covering and packing LPs. And that is what this is all about, right? But at least today morning when I was preparing for the lecture, I thought that maybe one can just apply like that also to integer, which is not true. But the first majority algorithm, we can change that to output me an ILP also solution. For example, what did we do for set cover, right? That is by nature, remember, that is by nature will return you fractional solution. But when you're doing this multiplicative weight update method to apply to ILP, what we try to do is to choose some set at every iteration or choose something integrally at every iteration. Okay, so we have partial integral solution. Some things are infeasible, and we try to some constraints are infeasible. We try to make it feasible by trying to apply some things, and this is what we saw that we could do to the set cover, right? And we analyze that way. So basically, there are two things to remember. Okay, two things to remember is in multiplicative weight update method, what is that it makes it all go through. Okay, so what is it that makes it go through is whether we apply to integer linear programming or something or to any fractional solution is its first is that we have some set of constraints or decisions, right? Anything, right? We started with set of decisions, right? And that is what we argued. And these decisions, and then we had these experts who were helping us to make this decision. So expert and decisions are something which are same, like synonym to each other. Choosing an expert means choosing a decision, because once we choose an expert, we followed him blindly. Now, in other settings, so this was our generic setting. Then we try to do it for solving LPs of some kind, right? Then it came up this. Now, the idea is that we have some goal or some optimization function to reach, satisfying certain set of constraints or certain set of cost vectors to minimize or maximize. And every time, so if you look at the proof works, we actually define an interesting potential, right? We define an interesting potential, and what are we showing in each round? Potential drops in some way. That is one thing, right? So we chose an interesting potential and we showed that this potential drops some way in an interesting way. Like for example, for set cover, it was dropping much faster, right? Like at e power 1 over opt, right? So this is why the number of times this happens is like opt ln n, right? So whenever we are going to apply this to ILP, the quality of the solution or the amount of sets you will produce or amount of things which you will output will be exactly proportional to the number of rounds of this algorithm, right? And somehow you have to argue that that gives you a correct answer. Okay, but with respect to LPs, I think there are better ways to understand this. Okay, and I will come to that in a minute, right? So this was governing T. Potential function was largely governing T, right? How fast this will terminate, okay? And the weights were determining the quality of solution, right? So phi determined number of rounds, and weight or probability vector, they are like, if you notice, they are just like same object in some sense, right? Or determined quality. So whenever in the expert setting, what we said, if some expert is going to be wrong, right? Let us penalize him, right? So we are giving importance to those experts who are giving us correct advice. So we are looking towards quality rather than this. And with respect to constraints, how did we expect? Say, oh, each constraint acts like an expert for me, and if he's satisfied, I don't want to pick him, so let's penalize him, right? So let's penalize him. So if I want to, like, so those guys have extreme high cost. So if my whole objective is to minimize the cost, it is better not to pick them, right? Like, only pick those constraints which have smaller cost. It is like, for example, if you want to look at your graph problem, you want to forward some vertex. What do? You just give so much weight that you never pick that guy. So what are you doing? You are exactly doing the same. You are enforcing that you don't pick him by giving him so much cost that if you are under minimization problem, you are never going to pick it, right? And for unweighted, we do some gadgeting that you never pick it, because picking him is too expensive, so that you can concentrate on those solutions which are still available and less expensive. So it is trying to mirror those kind of ideas. Okay. So the reason why I taught all these things, okay, so maybe next Thursday I will give you much more examples, not in this course anymore, except matching, for which I built all these things. Okay. And notice what is happening in certain sense, that every round when we are doing this LP, like, we are trying to improve the quality of the solution. Okay. So let's try to do matching and try to understand actually what is happening in this in a slightly different way. Okay. So if I have to write, say, I am going to take an example of say maximum matching in bipartite graph. Okay. So how will I write LP? So in bipartite graph, vertex cover and matching are dual to each other. So I could have written minimize summation xv uh, xu plus xv greater than equal to 1, and xu greater than equal to 0 for all v, for all uv in EG, right? This is one constraint. So this is nothing but a vertex cover constraint. Agreed? What will be the matching constraints? It's a maximization version of the problem. So this is nothing but max, okay, max summation, say yij, like for each edge, okay. I want to maximize, and what is the constraint? For every vertex we should pick at most one edge, right? So for all v summation, for all v, or say for all I in vertex set, j in a neighborhood of I, yij should be less than equal to 1 and yij is greater than equal to 0, right? So this is my constraint. This is like max matching constraint. Right? Right? Or in general, so this, suppose this is primal. What is this? This is dual, right? So in general, if I have minimize some C transpose X, Ax greater than equal to B, right? X greater than equal to 0. What is its dual? Is maximize B transpose Y, right? B transpose Y, A transpose Y less than equal to C transpose, right? Y greater than equal to 0. I think this is what, if you write it formally, this is what you will get it. Fine, sorry. Okay, so let me see what all things I don't need now. I don't need this, I don't need this, I don't need this. Okay, I explained this. Okay. Right. So this is what it is, right? And this is just one example of this. Now, what do we know from LP duality? We know that min summation xb is equal, or C transpose x, min of C transpose x is equal to max of B transpose y. Okay? Okay. So just to be consistent with my notation, let me write slightly differently. Somehow they write B transpose x so that I don't make mistake unnecessary. Okay. Okay, I'll tell you why I'm writing this. Okay. Because I am interested in maximization, so I want to call them I, so that this is A transpose, nothing more. Is greater than or equal to C, and x greater than or equal to 0. So dual LP is maximize C transpose y, A transpose y is less AY is less than or equal to B, y greater than or equal to 0. Okay, so this is what it is. And what we know, minimum of B transpose x is equal to max of C transpose y because of LP duality. So any value I can get here provides a lower bound of this. Any value I get here provides an upper bound on this. Like any feasible solution here, look at, okay, any feasible x gives us, for any feasible x, what do we have? B transpose x is less than or equal to max of C transpose y. So this provides a lower bound on this optimum value and the other way around. Okay. So if you have done primal dual algorithm, it goes in rounds and rounds, one providing a lower bound to the other till we reach in a place where there is some constant gap or whatever the approximation factor we are looking for, right? And if we are able to solve optimally, then there will be a time when both LP, primal and dual's solution will become equal, right? So now in this setting, what are these oracles doing? What is it trying to provide, right? Just try to think so that it looks a bit more natural than this magical, right? Yes, method is something, but what it is producing as a solution, like what it is giving to us, okay? Suppose here optimal solution is alpha, okay? Alpha. Suppose this is an optimal solution is alpha, right? For this minimization problem, okay? By the way, for bipartite graph, this is integral solution, okay? LP is integral for bipartite graph. I mean, it requires a proof, but I'm not going to prove that. So, okay, what will be the violation of dual constraint? So this is primal. Suppose, yeah, so this is primal and this is dual. So what is the violation of a dual constraint? What is the violation of a dual constraint? What it is? For some AI into y is minus okay. So this is a definition, okay. The violation of a dual constraint I is going to be AI y minus bi. Ai into y times bi. Okay. This is by how much it violates, right? And it may not violate at all anything when this is greater than or equal to 0. Okay. Now, what does complementary slackness condition tell us? Or condition tells us. Do you know what does complementary slackness condition tells us? If x is an optimal solution. Okay, or other way to say is that what does this means? For any optimal solution, x, okay, for any optimal solution x, okay, xi times ai times y minus bi equal to 0, right. If xi equal to 0, then this is 0, right. If xi is greater than or equal to 0, then this has to be 0, right. So I have just taken into together. So as she was saying, right, for any xi which is non-negative here, you have to go and look at the corresponding constraint here, look at the variable which is non-negative here, look at the corresponding constraint there, that will be satisfied with equality. This is exactly what complementary slackness condition tells us. Okay. So what is one way to express, let us put it this way, that how do we express this complementary slackness condition in just one constraint? Look, there are many constraints, right, many conditions, right, for each I this should be satisfied. Okay. Okay. So what I will do, I will treat these xi's, because they are we will always maintain xi as non-negative, because any xi is greater than or equal to 0, so there is no point going below 0, right. So xi's I will always treat, I will maintain them as a non-negative integer. And then how do I treat that? So like one way to express complementary slackness condition, okay, one way to like into a single condition is to treat xi's as probability, okay, treat each xi's as probability, okay, and ask, okay, and ask, is there a vector y, is there a vector y such that C transpose, such that I wrote C transpose y is equal to alpha, okay, such that the expected violation, expected dual violation is at most delta. Okay. So I think of these xi probability and I ask myself, fine, is there a vector y such that C transpose Y equal to alpha, so that the expected dual violation is at most delta. Okay, and this answer Y is considered as, okay, the answer Y is a dual witness. Okay. Now imagine I get an answer no or yes. So this is an oracle which I am going to ask. Look, whenever we were making this question, we had this oracle, right, for which we asked some set of questions. What does this mean when we are asking this set of questions to this oracle, right? What are we trying to achieve? What are we trying to get? Right? So what are the possible answers this guy has? No or yes. Either there is a vector y of this nature or there is no vector of this nature. Okay. So suppose it is yes, okay, and you have chosen probability mass in a way that it points us towards in the direction of those constraints which are violated the most. Look, if I chose this, like I think of this primal solution as probability distribution, and suppose I have chosen xi in a way, this is what we were trying to do here, like we were always trying to put mass on those xi's which were like less satisfied, right? So if I have more mass on those constraints which are not satisfied, then we have a direction in which to push things, right? And this is exactly what is happening in this oracle business, okay? And okay, do you understand? So if we choose probability, such that mass, probability mass is concentrated on concentrated on constraints with large violation, then what does it mean? It means I have some places where I could improve my dual solution, right? It points to the places where we could improve the dual solution, right? This is all that is happening in this oracle business, okay? So underlying principle is basically primal dual. That's all that I'm trying to tell you, okay? Right? So what does this does? It provides a direction in which feasibility of dual system can be improved. And if it says no, what is the meaning of this? What does it no means? There is no direction in which I can improve my dual solution. So what is the meaning of that? Huh? There is no feasible solution to whom? Of course, dual does not have any feasible solution. But what does that mean? You definitely know that dual solution, like with this additional constraint that C transpose Y should be equal to alpha, is infeasible. What is the meaning of that? Like, I mean, primal has? Why? Dual maximization problem. Primal dual is a maximization problem. Primal has to have a solution which is less than equal to alpha. It cannot be equal to alpha. Because primal had a feasible solution of value alpha, then that would imply the dual also has, I could use this translation to get a feasible solution for dual with value alpha. Okay? Okay. So, what could be a witness to one such thing? So, look, I know that this system is infeasible because with this additional constraint C transpose y equal to alpha is infeasible. What can be a witness for this? Can there be a witness for this? Suppose I had a feasible primal solution of value less than equal to alpha. What is the meaning of that? If I had a feasible primal solution of value less than equal to alpha, what is the meaning of that? Is less than equal to or greater than equal to. So, what you are saying that this quantity what you are saying that C transpose X this is less than, is this correct? Is this correct? Right? So, if you can come up with some feasible solution of value alpha, that gives you what? That tells you, that's a witness of the fact that this system is C transpose X equal to alpha has to be infeasible, right? So, this implies if we can come up with, alpha, if we come up with a feasible solution such that a feasible solution for primal with value alpha, then that is a witness that max C transpose X is less than equal to alpha, right. So, of course, it will not hold with equality. Okay. Now, but we are not asking the kind of question we are asking to our oracle was not like, hey, satisfied it with equality. We are happy with some approximation to right. So, these questions are not even well phrased in that sense, right. It is not even clear how will you get some feasible solutions or infeasible solutions just by using this method. And multiplicative weight update method is a methodology that tells you how to get some kind of solution in this kind of settings, right. If I were just posing this question to oracle and okay, it just shows me yes and no, this does not give me any method to find these x's and find these y's, right. But what is multiplicative weight method told us? Multiplicative weight method told us how to find such x's and y's like by solving this oracle. Okay. So what happens is that we are very careful in choosing the probabilities such that all the dual constraints like, or this is what multiplicative weight update method does, that we have a way to extract a dual solution which approximately satisfies all the dual constraints. Do you get my point? So at the end, what is happening? At the end, I gave you a solution. What is the property of that solution? In this method, at the end I returned you this x transpose this. What is the property of that solution? That approximately satisfies my, right, dual constraints. Okay. Anyway, we will see more applications next Thursday and hopefully it will become clearer. Okay. But what I want to now try to get to, okay, so this was just some general theory of why these things are the way they are, and let's start to understand these things with some of these things in our head and see what is happening, okay, with one concrete example, and then we'll come back and try to abstract it out. Okay. So first of all, suppose I have a bipetide graph and I want to approximate the number, okay, that what is the value of maximum matching up to say 1 plus epsilon, right? Up until now we know how to do factor 2 approximation, right? Just like greedily contain a maximal matching and very happy, okay. And look, in our algorithm somehow, look at our set cover algorithm, which approximately we just now gave approximation algorithm for that. What did we do? We knew that okay, opt is decreasing, so opt was using, but most primal dual algorithm works that by providing, I say look, here it is, here is a lower bound, and hence if I have achieved some factor times this lower bound, then that's my approximation ratio. So somehow in algorithm which are based on primal dual, they are making lower bound for whatever we want simultaneously at the same time. So we will also need to do that in our settings, okay, and we will see how to achieve this. So this is the matching constraint and this is a vertex cover in, right. So let me rub this out and let's try to understand the difficulty which we will face. So suppose I am only interested in solving fractional maximum matching. I can solve fractional maximum matching, right, and but look, here is space allowed, here are passes allowed. So if I try to maintain, like run these kind of algorithm in streaming setting, what will correspond to passes? This t, number of times we update. What is t doing? Each time you are updating your current solution, right? So t will correspond to the number of passes we are going to have, okay, number of passes that we are going to. Now we are solving just fractional matching, okay, fractional matching, right, and we will see how much space it takes, and passes corresponds to number of rounds. Now let's look at how many number of rounds this guy is going to take us, okay. We know if I just implement this particular algorithm, then it could take order. What was L and rho for us? It was, rho was basically the number of constraints. For the set cover, it was just the number of constraints. So like think even vertex cover, that is going to be something proportional to the number of vertices, right? This is what we did, right? What is an upper bound on the solution, which is n? That is what we use rho as. So I could use the same analysis and use the maximum matching size, which is equal to at most n or n by 2, right? Then already I have taken n rounds. No way I can avoid this, and epsilon square, epsilon to, right, and some more factors. So no way I can avoid taking this many space. But if all I am allowed is poly 1 over epsilon, right, then this is not good enough for us. I cannot just directly maintain this algorithm and hope to achieve this kind of guarantee. Do you agree to this? Right? Because this is going to like blow up the number of rounds. So I just cannot just run greedily this, okay? Even if I allow you unbounded number of space, I don't care about space, then only I can just store the whole graph, right, and give you the 1 plus close to epsilon solution to this, right? And the reason why a good 1 plus epsilon solution to fractional matching is also a good upper bound on the exact matching. Why? Because in bipartite graph, fractional matching solution is equal to integral matching solution. So if I told you the fractional matching has value this, I'm also giving you an upper bound on optimum matching solution. So this is why we can concentrate, this is why we are concentrating on maximum matching, because we will give an 1 plus epsilon approximation to the value of fractional matching, and that value of fractional matching itself is a lower bound on the maximum matching. If I say, oh, I will return a number n such that, say, return a number q, right, which will have probability, which has a guarantee that it is at least, say, fractional maximum matching divided by 1 plus epsilon, suppose. This is a guarantee. Then this is also the guarantee that optimum maximum matching divided by 1 plus epsilon, right? So it's good enough for us, at least in this setting, to get 1 plus epsilon to fractional maximum matching, and we will be good because these two are equal on bipartite graphs. For general graph, this is not true. Okay, so that's one point to note. Okay, so this is okay that we concentrate on fractional maximum matching, but if we do fractional maximum matching, if a space allowed is anything, then definitely you can store everything and solve it and give me. Pass is 1. But unfortunately, I am going to restrict you to take small number of space, which is order n, polylog n, and some, say, epsilon to the power big O of 1. This is what you are allowed to use, right? Now you cannot store the whole of them, and now still I want to take just poly 1 over epsilon space. Now the question becomes very difficult, right? So what do we have to do to this? Look at the phi value, phi, right? Number of rounds was guaranteed by the potential function and the drop in potential function in each round. If I can show that the potential drops way more faster in each round, that in 1 over epsilon, 1 over poly epsilon we will reach optimum, then that's great, right? Right? All we have to choose these things in a way that, look, T is just an upper bound on the analysis, but somehow if I can increase the rate at which we are losing the potential, right? Initially the potential is n and we reach 0 in, say, 1 over epsilon times. That's great, okay? But n could be way larger object than the maximum matching itself, right? So even if you go much faster with respect to n, expecting things to happen is not possible. But what we could use as a lower bound in phi? I just run first round of algorithm. For just first round, I keep maximal matching, right? 2 times that is an upper bound on 2 times that is an upper bound on optimum matching or fractional maximum matching. This I can achieve in 1 pass, no? Do you get my point? I run my first round and I just store greedily maximal matching of my graph. that will take n log n space, and I have just used one pass, but now I have a lower bound on the maximum matching, sorry, upper bound on the maximum matching, like by ratio just factor 2, because it's a factor 2 approximation. Now I will try to use that as my base point. Okay, so I already have factor 2 approximation, and based on that I will choose my weights, probabilities that it reflects that fact, and next you can only improve from this. So it's not that I'm starting from say one edge in my graph, like selecting and then making 2, 3, 4, 8, even with exponential increase, all I'm able to achieve is polylog n, right? Dead. It is an independent of log n, number of rounds is independent of log n, right? So the first thing is, but what does this depends on? What good quality solution Oracle returns? So if I have an Oracle which returns very good quality solutions every time, like it is really exponentially jumping towards the optimal fractional cover, right? Or let's say fractional matching is some delta, right? And I am guaranteeing that, and you are starting with delta by 2 because you started with delta by 2, and I am telling you that every time you at least increase your delta by epsilon times delta, right? You increase like at least by epsilon fraction you increase. So you started with delta, next you did epsilon delta, next you did epsilon delta, and so on and so forth. Even if I did this, I'm dead. Why? Because this is going to be delta by epsilon rounds. Right? Even if I increase by epsilon fraction delta each time, I'm not going to achieve much. So if I have to achieve epsilon, I have to increase by how much? Delta by epsilon every time, or epsilon to the power 1. I say, hey, my solution has increased like delta divided by some, not even 1 by epsilon, say 1 plus epsilon to the power big of 1, something of this nature, right? Then it is fine. Then maybe we will converge much faster. Okay, good. So let's forget. So you understand the idea of the algorithm, right? Right. But what is the hard part is, what is this good oracle? And what are the properties of this good oracle? Right? For matching, as I told you, right, I will start with factor 2 approximation in the first round, and this I can achieve in one round. Now, you can do much better, but what I will give you now is 1 over epsilon q times log n passes, and the space will be, okay, and somehow their language is like they are going to give you 1 minus epsilon times maximum matching, which is fine. Return a number which is at least 1 minus epsilon times maximum matching sign. So here is my oracle, and this is a magic oracle or not magic oracle. Okay. What is my probability Pi? So what does oracle takes? A number alpha, okay, and some probability vector, right? This is what it takes, right? Some probability vector, Pi's, right? Of the say tth round. So I'm going to write tth round. Okay, this is what it takes. Let xi equal to alpha okay. If I think of this as a probability, then why is this not equal to 1? Shouldn't be this equal to 1? No. Okay. So think that I give you weight function. Okay, I gave you a weight function. Okay. Otherwise, I should have just written. It doesn't matter. I mean, how do you choose it? So, but it might be a bit more explicit if we write like this. Okay, for convenience. Otherwise, the best thing would have been to write here. What do you choose probability? Is this? This is what you choose probability, right? Right. So basically, if I would have given probability, then I write alpha equal to pi. That's it. So if you think of the probability, but it will be good to assume that this is how the form is. It will be useful for computation, nothing more. Otherwise, you can think that this is alpha times pi of t for the ith constraint, right? Which corresponds to vertices. Where should you find maximal matching? Where? Think. Huh? Into? What is the violated constraints here? What are violated constraints here? Which constraints are violated? Why are they violated? Look, whatever it is, some things are violated here, right? A constraint which is violated will correspond to what? Which are? It is less than equal to 1, right? Sure. So what will that correspond to here? No, here in vertex cover, what will it correspond to? Look, they are dual to each other, right? So if some constraint is unsatisfied, what will it correspond to here? Can those constraints be satisfied here? Look at that vertex for which it is too much. Look. Why it should be less than equal to 1, but this is violated. So we need to make sure that, and why it is violated? Huh? Because you picked up lots of edges. Look, I have defined xi's, I have not defined yi's. I defined xi's, I didn't define yi's. Okay, it's 3 o'clock. We'll do it on Monday. Okay.